Good afternoon, everyone. My name is Stan Chung, and today I'll be talking about ultra-low loss and fabrication-tolerant silicon nitride demultiplexers for 1 micron CWDM or coarse wave division multiplexing optical interconnects. So as I outlined for today's talk, we'll first discuss some of the challenges and motivation for this work, which involves a low-cost, high bandwidth density CWDM optical engine operating at the 1 micron wavelength. Next, we'll discuss the design and measurement of various Gaussian flat-top AWGs and lattice filters, and we'll make some comments about the temperature dependence. And then finally, we'll discuss some schemes for 3.5 silicon nitride integration and packaging. So our charter at Hewlett-Packard Labs is to re-architect modern computing systems. And shown here on the left is a traditional computing system where information is chopped up to match the limitations of the processor. Essentially, the processor or SoC or system on chip is the gatekeeper. And so over to the right is our new memory-driven architecture where we flip the traditional architecture inside out and put the data first. And so we bring the processing closer to the data. And so this allows us to ingest, store, and manipulate massive amounts of data sets while simultaneously achieving multiple orders of magnitude less energy per bit. And so the photonics roadmap at HPE is aimed at achieving a low latency communications fabric that interconnects all the memory and SoCs together. And so our architecture is not limited by a specific form factor. It can enable communication between multiple system on chips, shown by the orange blocks, or inter-rack communication represented by the green boards, or enable communication between many racks and in a large data center shown in this diagram here. And so at HPE, we've developed an optical engine where we utilize 6 4-lambda lasers, shown by the rainbow blocks here, and they're capable of operating at 50 gigabit per second, giving us 2.4 terabits per second bidirectional bandwidth. Here we show our HPE designed ASIC, packaged with arrays of gallium arsenide VCSELs and photodetectors with a cradle around it for the fiber array attachment. And this is all designed for realizing a low-cost, high bandwidth density optical interconnect solution for memory-driven computing. So one of the key enabling components is the transceiver. And there's a need to extend data center distances while using our existing packaging scheme. So this entails designing a transmitter to launch into the lower order optical mode using existing data center multi-mode fiber or single mode fiber. So for the receiver side, we use current thin film demuxes for polarization diversification. And so some of the main parts are: 1, integrating low noise, single mode polarization locked VCSELs, and then coupling them into single mode silicon nitride multiplexers, which then couple the light into the lower order mode of a multi-mode fiber array. So why use silicon nitride? It has low optical losses. In our case, we measured 0.3 to 0.4 dB per centimeter loss, and that minimizes the impact to the power budget. The passband wavelength is tolerant to high temperature operation, such that tuning energy is minimized. And the medium index contrast allows for a relatively robust and process tolerant platform, at least for our application. And it's compatible with certain silicon photonics processes that may lead to interesting integration schemes in the future. Shown here is a wafer map of the thickness variation of the entire 4-inch wafer used at the Logitech foundry. The silicon nitride thickness is fairly uniform with a mean thickness of 148 nanometers and a standard deviation of 2.3 nanometers. So the reported width variation is about 13 nanometers, which is pretty good. So it's critical to understand the process variability on device performance, because phase-sensitive devices such as AWGs or lattice filters can be sensitive to phase errors, which are dependent on width, thickness, and refractive index non-homogeneities. The graph on the top left and right show the width and thickness sensitivity on the effective index. In fact, if you look closely at both graphs, the dimensional sensitivities are decoupled when the width is larger than 800 nanometers and the thickness is larger than 300 nanometers simultaneously, which is indicated by the blue regions. In our case, the single mode waveguide is 150 by 1,000 nanometers and exhibit effective index variations of about 6.4 e to the minus 5 per nanometer for the width and 1.2 e to the minus 3 per nanometer for the thickness. So as a result, the most critical parameter in controlling phase errors is the starting wafer thickness uniformity. We can also calculate the resonant wavelength sensitivity. In fact, we show that resonant wavelength is 16 times more sensitive to thickness than width. Here we present results of the measured 1x4 Gaussian AWGs over all dies. We measured 7 dies. They're designed for a channel spacing of 25 nanometers with the expectation that the center passbands will be centered from 990 to 1065 nanometers. And the best performing device came from die C2, which had a crosstalk level less than minus 25 dB with insertion losses less than 0.5 dB for the 4 channels. These responses are normalized to a 1 micron wide straight waveguide without an edge coupler, and so that represents the best case or the upper limit. Over on the left is a picture of the fabricated devices, and the AWGs are 200 micron by 600 microns in dimension. In this slide, we discuss some of the passband variation and uniformity measured over the 7 dies. This box plot over here illustrates the peak passband variation of the measured AWGs, and they indicate the process tolerance at Ligentech. So the mean wavelength peaks are located on the x-axis, and the boxes extend from the lower to upper quartile levels, and the orange lines represent the median. So this seems to say the process uniformities discussed in the previous section allow for making pretty reliable CWDM multiplexers. This figure here shows the calculated AWG passbands at 1040 nanometers with varying degrees of effective index variation, delta N. If we consider the corner cases in our fabrication tolerances, most of the effective index variation comes from the thickness variations, and that translates to index difference about 2.8 e to the minus 3, and then we can infer this to give us a crosstalk level about minus 30 dB, which is what we observed experimentally in the previous section. So if we can achieve an index level of about 6.0 e to the minus 4, we may be able to lower the crosstalk level below minus 35 dB. Here's a slide on the measured flat top AWG responses. And so from 25C to 80 degrees C, the Gaussian AWGs show passband shifts of about 1.05 nanometers. And the 1 micron pixels developed at HPE shift by approximately 3.8 nanometers. And so this precludes the use of using Gaussian AWGs unless thermal tuning or laser tuning is implemented, which further increases the power consumption of your system. So as an alternative, flat top AWGs were explored to reduce power penalty associated with high temperature operation. The idea is to use a somewhat flat electric field at the output place of the AWG using standard MMI, as shown here. So measuring over 7 dies, the best performing devices had crosstalk levels less than minus 20 dB at the center of the passband. Insertion losses can range from 2 to 4 dB for all 4 channels, which is expected because of the use of the MMI. As an alternative, cascade MZI filters have shown to be a low loss solution to realizing flat top CWDM demultiplexers. The table here shows that by picking the correct delays and coupling coefficients, demultiplexers can be constructed from a binary tree configuration of cascade MZI lattice filters. And so for this particular design, we show that we show such a filter using interleaved second order filters. And you can see that significant side lobes in the response from adjacent passbands can limit crosstalk levels to about minus 15 dB at the center portion of each channel. Now, if the directional couplers were designed to be broadband enough, the crosstalk can be theoretically be less than minus 25 dB at the center of each channel. For an alternative design, it consists of a cascade third-order MZIs, and the crosstalk level is improved due to steeper roll-off transmission of the multi-stage MZIs. And if dispersion is neglected in the power splitters, theoretical crosstalk less than minus 25 dB can also be achieved. So in this slide, we discuss improving the MZI lattice filter crosstalk. And high crosstalk exists due to the wavelength-dependent power splitters. So there's a need to design broadband process-tolerant directional couplers, or MMIs, but in our case, we just focused on directional couplers. Recently, bent directional couplers, shown in this figure here, have been proposed for broadband operation, and they work by designing for a specific coupling ratio while keeping the coupler length around the top portion of the transfer function, such that the coupling ratio is less dependent on the length. In orange, we have straight directional couplers, and this is all designed for 50%, and the blue are the designs for the bent directional couplers, and you can see that they operate over a wider bandwidth. If we look at the lattice filter response, we can see that the use of wavelength-independent couplers have a significant effect on the crosstalk levels versus lattice filters that don't have power splitters that are broadband. So in conclusion, we've examined silicon nitride CWDM filters operating from 990 to 1065 nanometers. We looked at some of the design sensitivities and correlated them to actual measurement results of AWGs and lattice filters. The Gaussian AWGs had crosstalk levels less than minus 35 dB, while the flat top AWGs had about minus 20 dB. Flat top MZI filters were measured with crosstalk levels of minus 15 dB and minus 20 dB respectively for the different designs. Temperature sensitivity was shown to be about 14.5 picometers per degrees C, which is 82% lower than silicon. And then broadband directional couplers were discussed and can be implemented to improve lattice filter crosstalks to, I think, about minus 25 dB. So that concludes my talk. Thank you.